Okay, now we're rolling. Okay, so no, I'm not gonna say it. I'm not gonna say it. But if you like that, hit the subscribe button. No, I'm kidding. Okay, so welcome to this 10th lecture already on natural language processing with deep learning. And I have to say something. So last time I think we did BERT. So we talked about the transformers and the BERT stuff, and the BERT transformer, which is the encoder, and we did a little bit of injustice to BERT. Not really being precise about a couple of things, and we left some things out, and I think we should really rectify that. We should really make it straight and make really, really, really clear what the architecture is, how it really works, so you can really do something with that. So we skipped some details about the architecture, which might be important and actually are important quite a lot. So something about this normalization stuff and the residual connections and things like that, which actually turned out to be very important. And we were unprecise with some graphical representation, so I tried to fix that. And we didn't talk actually, so one part was we didn't talk about this pre-training and fine-tuning. So we talk about multitask learning, so how pre-training on one task would be beneficial for another task, but we didn't talk about how it's actually done in BERT and why it actually was so successful when it came out. So let's fix this today. And actually, after this lecture, you should be able to build BERT with a little bit of trial and error, but you will have all the information that you can actually build this stuff. So let's have a look at the encoder architecture in detail. And at the end of the day, BERT is just a function. As every other neural network, it's a function. So it takes an input and produces an output. And it consists of some intermediate functions. And these functions, as usual, they are just differentiable functions with parameters. So you can train the parameters and you can differentiate everything from using the standard stuff we have. So once you put some final loss on the output, you can just do the backpropagation and to find how to update the parameters with stochastic gradient descent. Everything remains the same. I mean, the architecture is getting a little bit complicated, so it's not like one layer neural network anymore. It's just something more complicated, let's put it like that, and bigger, and also in terms of the parameters. But at the end of the day, it's a function which takes an input, and we will talk exactly what the input is again, and produces some output, which is also like a special form. So it could actually produce multiple outputs which are usable for different tasks. But eventually, it's just the input comes in. So the input are tokens, basically, because we want to run it over a sequence of tokens, as we said, and not about a sequence over the sequence of tokens sequentially, but taking the whole sequence at once and just run it through this network from here depicting left to right. And there's a couple of things that are some parts of that. So first part of that is how to turn these words, like the indices of words, I don't know, the cat set, into a matrix or a bunch of vectors. And then there is something which repeats itself in a way like there are some transformer encoder layers, and there is a number of them. So it's like a hyperparameter you can specify. So you say like how many of these same blocks you will repeat. But repeating doesn't mean they share the parameters. So they have different parameters. I'll highlight it later on as well, but just to make sure, there are several layers which have different parameters as in standard multi-layer perceptron. And then once you get some final representation, there is some sort of final projection to something which is interesting for you. So it could be projection into the vocabulary, like predicting a missing word or mask word, or it could be a projection into number of classes if you're doing classification. Okay, so this is like a high-level depiction of the BERT. So it's a function, takes a sequence of tokens and produces something which is interesting for us. And it learns some good representation of this input. So this is a high-level representation, okay? All good? So let's spill out also some sort of like a formal algorithm as a function. So let's start step by step. So we will call it this function e-transformer. So it takes the input, and these are some parameters of this network. Okay, so a bunch of all these weights and biases, and we'll talk about it in detail. But basically, this is the input, and this is a sequence of token IDs. And if you remember the exercise from yesterday, what we try hard is to change the tokens. So in our case, the tokens were what? What was the tokens yesterday? What were the tokens? We build a vocabulary of tokens, but the tokens in our case yesterday were.
Yesterday we used characters.
We used characters yesterday, okay? So we build a character and each token was a character. So we had a sequence of characters. Typically, what we have here in transformers is something else. So we can use words, but we can use also something else. Something in between characters and words. So what is it? Do you remember? What is the unit between? So you can chunk your text in words, in tokens. I mean, basically by words, by white space. Or you can chunk it into characters, but maybe you want to do something in between. So how is it called? An engram is a consecutive, like two consecutive tokens. I would call it engram. Yeah. Maybe it's an engram of characters, maybe, but it has okay. Yeah? So it's a some sort of a sequence of characters. So do you remember how we call that?
I'd say you're looking for subword tokenization.
Subword units, exactly. Subword tokenization, exactly. So we didn't chunk text into tokens, into words by white space, but we chunked the text into like subword units. For example, splitting the words in the middle, like sitting would be sit, ing, like double SITT, and then next token would be ing. So we had like multiple, each word would consist of one or multiple subword units, okay? So we had I think we discussed it quite in detail in one of the earlier lectures, like the second one. So you might want to refresh that. So this is the input, a sequence of tokens, and these are token IDs, and these would be like subword units. And we had algorithms for doing so, such as BPE, so byte pair encoding. We talked about it, and we had also sentence piece. And these are something you should know. So sentence piece and BPE. Sentence piece is just a standard kind of thing of doing subword encoding nowadays. So each sentence piece unit would be associated with an integer, so an ID. And this is what we had yesterday. So we had each character from vocabulary was associated with an ID, and that's why we were indexing the matrix. Anyway, so this is the input. Any questions? Okay. And the output is typically for each token input, we get an embedding vector. Typically. So this is what you want actually. So if you remember, so what was word embeddings? The static, like word to vec, what was that? What was word embeddings? Word embeddings, what was that? Yeah. It's okay, so we had a word and it has a representation as a vector. And there was something special, like one advantage or maybe a disadvantage of these static word embeddings. What was that? Yeah. Yeah, we could. So we had some relation. We had some notion of similarity. So if two vectors are similar, then maybe the meaning of these words is similar as well. But there was one really disadvantage. So if you remember the word bank, if you look up like word to vec bank, you get what? You get one vector. But yeah, there are multiple meanings of the bank, right? So you don't get like disambiguated meaning of each word. So you just get like for each word as represented lexically, like B-A-N-K, you get just one vector. But words have different meaning in different contexts. So one, bank could be what you sit on and stuff like that. Okay, so polysemy. And here the BERT model is excuse me, the BERT model is outputting embedding vectors for each input token, which are context dependent. So for each word, you will get an embedding, which takes into account all the other tokens in the sequence. So these are basically contextualized word embeddings, which gives you much better representation of, because then you can really disambiguate like I sit on the bank. So for the word bank, you get an embedding vector, which will be much different from I went to the bank. And this is what you want, because it gives you like much more better representation of the true meaning of these things, okay? So typically for each token, we get a embedding vector. And we might also then turn each embedding vector into excuse me, we can turn, yeah, exactly. We can turn embedding vector into a probability distribution over words. So here Lx is the length of the sequence, and Nv is the, what could that be? Size of vocabulary. Size of the vocabulary. So the vocabulary are the support units, and this is the size of them. So we can turn each vector into basically a probability distribution over words, which we use for basically predicting the probability of the word appearing at this position. We will use this for actually pre-training the model. But I just wanted to say, like, typically you might use the embedding vectors, but when we're training, the output of BERT is also turning these embeddings into the distribution over the words. Okay. Any questions? Okay, so this is the input. I mean, we started the function here, so this is just saying what's coming in. So we have input and parameters. So let's go step by step. So let's focus on these input embeddings. What is that? So the idea here is taking the sequence of words, like the tokens. Here in this case, I'm using just words. These are no subword tokens. And it could actually be that the, cat, and set are present in this, in the sentence piece vocabulary, because these are short enough and common enough to be actually part of that, right? Because we're building, if you remember how we built these byte pair encodings or sentence piece, we're merging very likely occurring sequences of first characters and then more characters and more characters. So we might end up with the, cat, and set in the vocabulary. Anyway, so each of them has this ID. So the V is associated with 21, and cat is associated with another word. And well, this is something like, one-hot encoding. I mean, in one-hot encoding, you would like position of the word in the vocabulary, the same thing. Each word has an ID. Okay, so we turn it into IDs, and the maximum ID would be the size of the vocabulary. Okay, cool. And that's it. So we have a vector of some length, and the length has to be specified as so there's some maximal length of the BERT. But let's say it's shorter now. So we have a sequence of 3 words, and we turn them into input embeddings, which means each of the words now is becoming a row in this embedding matrix. Okay, so it's vector is coming in, and a matrix is coming out where this is a embedding of the first word. This is the embedding of the second word, and this is the embedding of the third word. Okay. How the embedding looks like in detail, we'll look into that. But just in an abstract level, we're just turning the word into word embeddings and just stack them together. So this size is basically input length. Okay? Cool. So let's do that. Let's look how exactly in BERT are these token embeddings done. So we continue this function, and okay, so let's okay, so we need to know the length of the input. So we call this this beautiful I don't know the name of this shape. It's L math. You write it as math calligraphic L. Yes. So this is the beautiful calligraphic L, which is the length of the input. Okay. And then for each position, so what was that again? I mean, do you remember how what this mean? Like if we say for I in, let's say, N, what does it mean? Like this notation, we used it last time to make it shorter. So it means basically for I in 1, 2, 3 up until N. Okay, so basically it's just shorthand for all indices in 1 to this number. So it means like for each token now, so for each token, we create the embedding. Okay, so for each token, we create the embedding as we had before. And the embedding is a combination of 2 things. So one is the actual token embedding. So what does it mean? So this is a matrix, W, okay, what is it? WE. WE is going to be a matrix of embeddings, which has, I guess, this is going to be size of the vocabulary, and this is going to be some sort of dimensional of the embeddings. So what is this saying? Well, take the word, the index of the word. So if I don't know, if xt is, what was the first word? 21. So take the 21st row here, and this is going to be the embedding. Well, this is the same as we had in the standard neural language model and word embeddings. You basically select the row of this word from the word embedding matrix. Okay, makes sense. So this is the notation we're using. So take basically the dot means like all columns. So if you're familiar with NumPy or indexing arrays in NumPy or Torch, this is how you select one row from a matrix. Does it make sense? Okay, so this is the first part. It's taking the first, so basically the row, and then we're doing the same for WP. WP, but WP is something else here. Oh, this is interesting because we're taking, so what is T again? T is a integer, and this is the position. Okay, so the position could be something from 1 to the length of the input. So let's say our position here for the word D was 1. Okay, so let's say T is 1. So we selected the 21st row because the word has index 21. And now here from the other matrix, which has different shape, well, at least different number of rows. This is going to be ED. Otherwise, we couldn't just sum them up. But here, well, what is this going to be? Because we want to do for each input sequence, for each input position, we want to select here a embedding vector. Any idea what this could be? Yeah. Exactly, that's going to be the maximum length, because for each token from the 1 to L max, we need to select an embedding. So it's going to be something like L max, so maximum length. So here, it's the size of the vocabulary, but here it's the size of the input, the maximum size of the input, which could be in BERT was something like 512. So, and now if we are in the first position, we're taking the first row and sum them up. So summation, okay? So we have two matrices of embeddings. One is a lookup embedding for the token ID. So for example, here, this is token of cat. Oh, sorry, excuse me, for the. And this is embedding for position 1. Then if we take maybe the second word, which was, what was that? Cat was 11,000 something, 11987. So in the next step for t equals 2, we would have this. So cat and position number 2. And we would sum them up. Okay, so this is how we get the embedding of the second token. If I come back here, so this would be the sum of the two rows from both matrices for the first token. This would be the sum for the second token, second token, and this is for the third token. Okay. Any questions? My question is, where do they come from, these matrices? How do we find, what are they? Where do we get them?
Visualize them with random weights.
Okay. Exactly. We made them random at the beginning, and then these are parameters of the model, so we just let them train on something which we'll discuss later. But these are just the standard parameters of the model, trainable weights. We learn them by doing some task, okay? And there will be initialized as random. Okay, so this is how we get for each token, and then as we saw here, we want to make it a matrix. So basically we stack them together. So we're stacking row by row this vector to form a matrix. Okay, so if we see this X matrix, it's a stacked word embeddings for each, the token embeddings for each of the position. So each row corresponds to one token from the beginning. Okay, so this is how we stack them together. I mean, stack row wise. Any questions? Sounds doable, right? I mean, it's just, this is the first step. Okay, cool. So let's move let's move on where we were. Okay. So we talked about the input embedding. So this is done, right? I mean, we have the input indices, and now this is a nice matrix. So the matrix has some properties. What's the dimensionality of the matrix? It's how many rows? How many rows does this matrix have? So it's the input size times some embedding dimensionality, like DE, right? I mean, this is it. So we have three rows and some predefined number of some predefined dimension of the embeddings. So this is the row. Okay, so we talk about the embedding. So now we're having a matrix where each row corresponds to a word, and then what we're gonna pass it through is a bunch of consecutive layers of the same architecture. They will have different, they have different parameters. So it's important to remember they have different parameters, which means if you think back about the RNN, in RNN, we also were going from one step. RNN is something different, but in RNN, we are sharing the parameters. So in each step of RNN, we are sharing the same parameters. So there was some repetition of parameters. Here, we don't share these parameters between these layers. It's conceptually very different, okay? So they will have different parameters, which means if you want to add more layers, your model will grow because there will be more parameters to train. So it's going to be costly. So the L, how many transformer encoded layers you're going to stack in there, it's, I mean, maybe you want more, maybe you want less, but at the end of the day, you're limited by your GPUs. Okay, so typically, I think in BERT, the number of layers was 6 for the small model and 12 for the biggest model, for the BERT large. Okay, so this is some hyperparameter, and you need to think wisely because training takes maybe, you know, instead of like 3 weeks, it will take like 6 weeks with more layers, and it just won't fit your GPU because it's just too big. So it's a hyperparameter. So it's repeated L times, and I think now we should look into one of those transformer encoderless layers, okay? So here's again the loop. Okay, so we have this X matrix coming in, and we repeat for 1 until L some operations. So what are these going to be? So let's look at the single transformer. Just one now. Okay, so it's this is like a zoom in to one of these blocks. So what it means is we have X is coming in, excuse me, and X is coming out. Well, I mean, it's not the same X, but it has the same shape. Okay, so it has the same number of rows and the same number of columns. So what was it again? It was length of the X times some dimensionality of the embeddings, something like that. So the same shape is coming in and the same shape is coming out. Okay, so, and here's a couple of paths it's taking. So we should start from the beginning. Like let's dive deep into this box. So here the X is going through two paths basically. One is this multi-head self-attention. We talked about it last time already, but I guess we should fix a couple of things in there maybe. And there's also just going directly to the sum. So this thing is called we call it residual connection as well. So it's one of the terms. And it means like, well, there's a direct path from the inputs to, you know, later to this to the next parts of the network. And we're adding something to there. So we're adding some input from another block here. So from the multi-head self-attention. Okay, so there's two paths. Is it possible to build such a thing? I mean, yes, because it's a directly acyclic graph. So there's no loops, there's nothing. And if you do backpropagation, well, you know, we implemented the sum node in the very first exercise. So you can do partial derivatives of sum node with respect to everything which comes in. So everything will backpropagate properly, and so it's basically a acyclic graph. So it's a computational graph. Everything is computational graph here. Okay, so you can do that. So let's have a look at a multi-head self-attention here. But let's just let's just make sure that we have this first part of the algorithm. So we're gonna take here we're gonna take X and sum up with the output of this multi-head self-attention. So in the algorithm, it means, okay, X plus multi-head attention X. So this is the residual connection, exactly. Okay, so now the question is, well, like, what is in here? So multi-head, and in this case, it's still unmasked, which will, well, it's not important today, but will be important in maybe in next lecture. It's multi-head self-attention. And what does it mean is that this X input is going to be run in parallel blocks, which we call a head. I don't know why it's called a head, actually. Maybe there's a reason. Maybe somebody came up with this name. I don't know. I mean, it's just a parallel block. So the X is going in parallel blocks, which is, there is H of them. So H is some hyperparameter. And it could be something between, well, actually, I don't remember what was in BERT, something like maybe 12 or 24, maybe something like that. So it's not hundreds. Why? Because there's some huge matrices in each of them. And again, like there are parameters, because as you remember, I mean, the green ones are functions with parameters and the blue ones are just functions without parameters. So these are trainable. And there are some parameters, and if you add more parameters, your network will grow again. So if you want to run like 120 layers, 120 attention heads in parallel, yeah, good luck. If it fits your hardware, then maybe it's better, But again, you're limited by your size of the hardware. So this is another like hard constraint, I would say. Like it gives more expressiveness to the network, but it comes with the cost of computing cost or training and inference as well. Okay, so but conceptually, we're running through parallel heads, and each of them is producing some output. So the output it's not the same as X, so it has different dimensionality. We're gonna take these outputs and stack them into one matrix, Y, and then we wanna project into the same sort of same dimensionality as the input, so there will be a linear layer. So what is a linear layer? What is a linear layer? If I have an input, say, I have vector A, B, and C. What is a linear layer doing? Like, what is conceptually linear layer? You have a vector, and you're gonna do something with this vector.
Bilinear transformation.
Which is
No, we can represent by matrix.
Exactly.
It's just
yeah, exactly. It's just multiplying by matrix plus some bias. Okay, so this is a linear layer on a vector. Oh, but here the Y is a matrix. Well, anyway, so you can DEF. You can run, if you do matrix by matrix multiplication. You take the second vector, multiply. At the bias, I think like the bias should be like adding to each row, right? So multiply the second by the matrix and add the bias, and you get the output as you want it. Okay, so you basically multiply one matrix by another matrix, and each matrix row represent these are multiplied independently. Each of them is multiplied independently, and maybe the bias could be added to each row because you might want to have just a single bias. Okay, so these would be the weights, and this is the bias. You know how to apply it for one vector, so it's a linear projection. And on multiple vectors, it's again multiple projections of each of these vectors. Does it make sense? All right. So which means if we have vector here, we can project it into X and make sure that the output dimensionality of X is matching the input dimensionality of X. Okay, so this is how we end up with the same dimension. So conceptually, excuse me, conceptually, we take in the input and send it to some parallel workers, and each of the workers does something, which is the single attention head, comes with output, we stack it together, and then project it to something which we want. Okay? Cool. So the question is like, what is in here? What is the attention head? So let's zoom in. Oh, no, okay, wait a second. Yes. This is the algorithm for the multi-head bidirection. Okay, so this thing, the whole thing is now specified here. I believe we introduced it already in the last lecture. Maybe, maybe not. So don't be scared by, okay, so you can ignore these parameters. I mean, this is just to make sure that all these weights and biases and things just match. You know, you have some reference of the dimensions if you really want. But what's important here, you take for each h in the number of layers. So h is in 1, 2 number of heads. You run the attention, the self-attention here, and then this is stacking together as before and applying the linear operation. Okay, so this is just spelling out the algorithm as we have it graphically here, just as a algorithm. And here you see, like, you know, the dimensions of the intermediate outputs, because there's some other dimensionality you can specify. The size of this matrices is also important in terms of also like computational power or expression power. Okay, so this is how you would build this multi-head attention. But the important part is here, like the self-attention. So what does it mean? So the self-attention or attention head is just this one single block. Okay, so let's have a look into this one block. Any questions so far? So again, let me just rephrase where we were. Okay, so this is like this is the whole thing. Now we're looking in the transformer encoder layer, one of those. So there is 1 to L. Each of them looks like that. So it starts with the residual connection and multi-head self-attention. And now we're in this multi-head self-attention, which is parallel couple of these heads. And now we need to look what's inside of each head. Okay, are you still with me? Good. So it's like zooming in. So let's zoom in. Okay, so what's the input? So okay, let me just come back. So the input is X, and the output is some sort of Y matrix. And the H means it's just, you know, the index of the head. So to make it sure, there's nothing special about it. It's matrix in and matrix out. So again, what is this X matrix? What was that? So this was, anyone remembers what was this X matrix? We talked about it like a couple of times already. So what is in there? So it's a matrix where, what is here? What's the size of how many rows does the matrix have? Yeah. The length of the input, yes, exactly, because each row in this matrix corresponds to one token from the input. So this is Lx. So each row basically here still corresponds to the input, to each token. And what was this? I guess was some sort of attention dimension, some hyperparameter. I guess we can figure out it here. Yeah. Dx. Yeah, okay. So some sort of dimension which we specify. Okay. So, but the important part is this, like each row corresponds to one token. And like the cat said, okay? So now we're coming to this. So we discussed it already last lecture, but I guess we should, you know, it never hurts to make it like take a different perspective. And I try to make the visualization precise this time, like very much, and even the algorithm. So we take the X and do some projection. Okay, linear layer, linear projection. Now what is linear projection? Well, we just multiply by a matrix, right? We had it already. Okay, so this is, oops, excuse me. Yeah, anyway, so we just project it to some other matrix. Okay, so this will be a linear projection. And this is the query. We project the same input to, again, another linear projection. So these have parameters, right? But these parameters are different, obviously. Like there are some matrices. We project it to another matrix, which we call the key. And we have the query and key. So now, with these two matrices, we make this scaled product. So basically, I think we have this here as well. Now, we discussed it last week already. So where you take each row from the query, so if this is Q, something like that, and this is the key, you transpose it, so you have the same, you know, you can do the dot product and do the dot product for each row and each column, each row and each column, and so. So you end up with a squared matrix of the self-attention. So this is basically a raw, and we use this. Why is it scaled? Because we divided each number by the number by this. What was it? 1 over square root of d for some numerical stability reasons. Okay, but basically this is taking the query and a key, and taking the dot product of each vector from query and key. So we end up with this matrix. And then what we had was we run a softmax on each row of this association matrix to make it sort of make it probability distribution. So make it sum up to 1, right? After softmax, each row sums up to 1. So it's something like a histogram and so on. And after that, okay, so we end up here. So we have some softmaxed dot product scaled. And we need something else. We need a value. So the value is, again, a linear projection of the input. Okay, here, so this is important about the self-attention head, is that query, key, and value are coming from the same input. It will be different for other models later on, like maybe an encoder-decoder, but now everything is coming from the same input. So again, we do a linear projection of x into the value. So it's called the value. And now having the value, we're gonna weight basically the value by these associations. So by this matrix multiplication, we're changing the value in a way that it takes into account these probabilities, so the influence of each other token on each particular, let's say, entry in this value matrix. Okay. Does it make sense, or shall we spend more time on this? Or having like a work-through example? It's an open question. I mean, so is it clear? Because we talked about it last time already. We talked about it like again. I don't know. So do you want like a workout example or more explanation, like why this is like that? Yes. Yes. So what do you want to know? What you don't understand about the query key and value? How do you split the x? Okay, so you don't. Oh yeah. You don't split the. Okay, well, you don't split the x. You have x in the attention. So let me just come to this function. Okay, so ignore the parameters. Input is x. So this is what's coming here. And the output is some output of the attention head. So I call it v here, but it should be some. Let's call it y now. Okay, y h. So the input is a matrix of input times some embedding dimension, and the output is again the output of the input. The length of the input times some other dimension. And what I'm doing here, so I mean splitting, this is just graphically saying, well, I'm sending sort of the input to 3 different blocks. What does it mean? I have 3 functions that are just independent of each other. And I'm saying, okay, here for the query, multiply the matrix. So it's a linear projection. Multiply the matrix, multiply the input by matrix and add a bias. Exactly, it's different ways and different biases. Okay, so for the query, I have it's differently parameterized. And for the key, it's also differently parameterized. And for the value, it's also differently parameterized. And these things will be learned, right? These are learnable parameters. Does it answer your question? Okay, any other question? So let me just come back here maybe, or, yeah.
In the graph, the matrix multiplication is being, so it says that it would be a trainable function, but in the next slide.
Oh, okay, yeah. So this is not, this is not trainable. This is a typo. Not trainable. So if you're brave enough, you can just create a pull request on Git and change. There is one line in the slides saying haram, and you can change it to neuron, and it will change the color of the box. And if you render these slides again, you will get the proper color. So this should be blue. Okay, sorry, yeah. Should be blue. Yeah, that's a good catch. So that's not trainable because there's no parameters. There's no parameters here in this in this multiplication. That's correct. Thanks. Cool. I need to fix that. Fix me. If you're brave enough, just open an issue on GitHub so I don't forget it. I mean, it's, you know, that would be really appreciated, because I'm not gonna just watch this, you know, the full lecture afterwards to fix that. Okay, anyway, any other question? Yeah.
This is computation invariant.
So this means it doesn't really matter. What you're trying to say is it doesn't matter where the token is in the position, you know, on which position the token is, or because if, yeah.
Swap the input,
Mm-hmm.
the outputs get swapped, but the values don't.
Exactly. That's true, because all these multiplications, if you multiply a vector, excuse me, if you multiply a matrix by a matrix and you flip these two values, then there will be flipped in the output, but the values will be, you know, their content will be the same. So this self-attention doesn't take into consideration where the input is. Is it like position 1 or position 2, position 3? Okay, that's true. So you see the problem here? Well, maybe that's not a problem because it's already fixed by introducing these position embeddings. So we kind of need to encode on which position the word was, because otherwise it would be like, you know, a time invariant or time step invariant or permutation invariant. So you can, I mean, you can prove it. I had it in one lecture, like in Munich last semester, basically proving this invariance. So if you wanna see that, like look up these lectures. But I didn't find it super exciting for the lecture actually to show like 3 pages of proof that if you flip things, it will be differently. So that's why, you know, this is like important detail of this, like this, all these multiplications are permutation invariant, because if you permute the input, the output will be the same, but it doesn't take care into this doesn't consider the actual ordering here, but you care about the actual ordering by introducing the position embeddings at the very beginning. You know, this was the same problem with the convolutional neural networks for we talked about this last time for machine translation, where actually these positional embeddings were introduced first to work with convolutions, because convolutions also are the permutation invariant or time invariant feature extractors. Anyway, so this was a comment, not a question, right? Yeah, okay. But I think it's important to stress it. It's an important detail. Yeah. So any other questions? Okay, so that's great. So here's how it's actually, you know, could be implemented. So we have 3 linear projections. Here's the dot product and scale dot product. So we're scaling by the size of the the square root of the dimensionality of the attention, and here we're running the softmax over each row in this in this scale dot product. We run the softmax and then weight by this value the output matrix. Okay, so this is very deep in like one attention head. Okay, but now, okay, let's come back. So where we were. So we had this multi-head self-attention. We look into how it works. So basically we run this several times in parallel, each of these attention head. And then we looked into what each of these attention head is doing. So this is a like self-attention head. There's no masking. So we're getting something out of here, which we then stack together. Here we stack together, make a linear layer, and coming back, we can make a sum. Okay, so we are zooming out now back to this one layer of the transformer encoder. Okay, here's the again. So we had the input, we know the residual connection. Now we talk about the multi-head self-attention. And what's outputting here is again like the same sort of dimensionality of the input. Okay, so this is the same matrix. Again, each row corresponds to one token from the input. Cool, so we sum them up. Okay, so then up until here should be more or less clear. So it maybe needs some time, maybe some examples to go through, but conceptually we know what we're doing. So we have this several attention heads, and the more attention heads, the more expressivity, but it comes with a cost. So let's add layer normalization. So here's other things. So now we move on in the network, so to say, and we're normalizing layers and then do something else. So let's have a look at this layer normalization, and then later on this GALU thing, which is new. So we talked about actually layer normalization already, and just a quick recall. So it's just a fancy word for making a vector centered around 0 and having a standard deviation of 1. Right? So basically, if you have, I don't know, let me just graphically try to, if you have a, so this would be a vector, and here one value, so these would be position in a vector, something like that. Okay, so this is like a 0, and this is like position 1 in the vector, position 2, position 3, 4, 5, 6, and 7. So you want to change it that it's centered around 0, so it'd be like that, this, and scale down. So the standard deviation of that would be 1, something like that. You just basically shift it to 0 and rescale. So it's centered around 0 with some standard deviation. Okay, graphically, or I mean, this is very bad graphics. I'm sorry about it, but it's just kind of maybe explain the mathematics behind. So how we did it exactly was to first find the mean of all these points. So what is this average? Which means then we can basically subtract the average here. Then we subtract the average from all values, and this is to find the sample variance. So what is the variance of this, and then we can scale it down to this, to standard deviation of 1. Okay. So this is basically shifting and rescaling. What are these parameters? This gamma and beta means that we can actually, to each position, we can maybe multiply it by something. So scale it to something else, maybe, and also shift it by something. So we can basically, first we take these values, cram them to be around 0 with standard deviation 1, and then we can undo this operation by shifting each of them and scaling each of them. Right? And these are trainable parameters. So we train this. And some networks don't use this, like they use gamma of 1 and beta of 0, so not trainable, basically only like normalizing, but some architectures are actually training this scaling and centering and unscaling, uncentering. So you can train this, okay? So it's just a parameter. Can you do this? Absolutely, it's a parameter. So this is just a differential by function again, and you can just learn it by backpropagation. Okay, any question? So this is done on one vector, okay? And what we actually doing in layer norm, I call this here layer norm each row. So if you have a matrix of, I don't know, the X matrix was, token 1, token 2, token 3. So this is a vector. Well, we apply this layer norm to each vector independently, and that's it. Okay, so it's just per row. So we take each embedding of each token, do this rescaling, shifting, and maybe again scaling and shifting, but we do it for each row independently. Okay, so it just that's a layer norm on a matrix, basically. Any questions? Okay, sounds good. So what do we have? So we have a layer norm. Okay, so this is done. So here the matrix is coming in, and it's a little bit changing the values by these kind of rescaling and shifting. Okay, but there's no other projections. So, and now we are taking two paths again. So one is going to be again to directly go to the sum, and one is going through something else. So you remember what this could be again? What was the name? Like if you sum directly the input and do something else with the input again and sum it together, this was again like a residual connection. Okay, so there's two flows of the input. One is direct flow and one is through something else. So let's have a look at this something else. Okay, so we have something else. So it comes a matrix in and comes a matrix out. And it consists of linear layer, then GALU, and linear layer. So we don't know what GALU is. What if we just say ReLU? Okay. So what is this thing? It's a linear layer, then ReLU, and then another linear layer. What is it? It's a basic building block of deep learning. What is it? Yeah. It's a multi-layer perceptron, exactly. It's a multi-layer perceptron or feed-forward network. It's a multi-layer perceptron. It's a one linear projection, non-linearity, another linear projection. And you can stack these layers maybe to make it deeper, so multi-layer, but it's just a simple one layer, I guess it's one layer perceptron. I'm always confused by the terminology, you know, how many hidden layers you have in multi-layer perceptron and stuff like that. But it's basically one non-linear projection followed by another linear projection. Okay, if we had a ReLU in here. So if you don't remember multi-layer perceptron, go back to lecture 3 and 4. These were the basics. So where you take the input, project it to something else, make some wrapping in the space, project it to something else, and do your stuff. So this is what we have here: multi-layer perceptron, like basic block of learning projections in a wrapped space, so to say. So okay, we had ReLU. What was ReLU? What is ReLU? Whoa. Whoa, whoa, what is ReLU? Okay, I want to see all hands. Okay, in the back. It's a nonlinear function, so how does it look? Okay, so if let me just write it down. So if the value is bigger than 0, it's the value, so it's like identity here, okay? And otherwise it's just 0. Okay, this is ReLU. Exactly. Thanks. So, you know, you should know ReLU. I mean, you should really know ReLU. Okay. So this is ReLU, and now we are talking about GeLU. So it's going to be something very fancy. Let me come to GeLU. Okay. Let's just start with the graph here. So if I show you this, what would you say? Like if you zoom out, what is it? If you zoom out a little bit, it's ReLU, right? I mean, it's 0, and then it's identity, okay? Roughly, but it's not, because here around here it's some sort of like a soft knee. So you basically go a little bit down and up, and you know it's making not this brutal non-differentiable point. I mean, it's not, yeah, it doesn't have a derivative at 0, I guess, right? Because there's two limits from different sides. So it makes it very soft. So there is a derivative, you know, the derivative changes slightly at all the points, and you know, things like that. Empirically, it was introduced by these people in 2016. It was then actually repurposed by Google under the name, I guess, Swish, maybe Switch. I don't know. If you look up this paper, actually, there's a discussion about how these ideas were kind of borrowed but not cited by Google, introducing by Swish, put it into BERT, and then basically undoing, well, whatever. So there's a story about like story about science, how things are getting cited or not, how you kind of ignore ideas or you're not ever about ideas and do it by your own and stuff like that. So this is in the appendix of this paper now in archive. But anyway, and it's been compared to other like ReLU and other TAN-H and stuff like that. It empirically was better. So this is the thing. Like it looks the same like ReLU. It's almost the same, but empirically worked better, so people just adopted it. Is it the best activation function ever? Who knows? Maybe for some tasks, maybe for some not. So how is it done? Let me just delete this. What this GeLU is doing is something very fancy, like mathematically, because it says the GeLU is the value of the function, and then it's a continuous distribution function of standard normal of this thing. Okay, well, what is this? Okay, so standard normal. So so you know standard normal, right? I mean, if you have a probability density function of standard normal is this this hat. Everybody knows that, okay? You might know the formula of standard normal, like 1 over squared 2p, blah, blah, blah. So what is CDF? What is CDF? So this is PDF, probability density function. What is CDF? CDF is a continuous density function, and it's saying what is the value, what is the probability of the value being less or equal than the value. So CDF is basically something like that, and then it grows here, and it almost reaches 1, and then it's almost 1 until infinity. Okay, so this is the CDF of Gaussian. If you look at Wikipedia, you'll find what CDF is. So, and there's actually there's a relation between PDF and CDF because one is derivative of the other. Okay, so there is some basically CDF is derivative of the PDF. Anyway, so what's important here is that the CDF is some sort of, it almost looks like a 0, 1, but it's not. So it's almost like, you know, if you scale out, it's almost like 0 and 1, which gives this. So if you take a number here and multiply this by itself, by the CDF, you get mostly 0, 0, 0. Here it will become something maybe negative, and here it will be positive, and then it's multiplied by 1, which gives you this sort of knee. Okay, so if you work out this formula, you will get some nice knee around 0, and the rest will be just, this is almost 1, this is almost 0, so you get ReLU. Okay, so this is like fancy thing of computing, and this looks like very, so if you need to evaluate it, the CDF, this is this very ugly integral. Can you evaluate this integral? Can you solve it? I can't. So there's no closed form solution for this integral. So you need to, like, if you need to solve this for x, you need to do like numerical solving things. So there's no closed solution for that. So that's why, I mean, and there's a way to compute this integral or the CDF by using so-called error function, ERF, which has like very fast and precise approximated implementations. Doesn't matter. If you want to do it like, if speed in GALU is better than being exact on the value, it's basically using approximation with a sigmoid. And sigmoid is nicely evaluable and differentiable. Okay, so basically, if you want to do it, if you want to knee and do it nicely and fast enough, then use just sigmoid and this. Okay, so these are very ugly details, which are maybe not important, but that you know, yeah, okay, so some functions behave better than the others, and empirically it was found to be GALU is one of those things. So if you see GALU, you're not scared of. It's like ReLU, but it has some other properties. Like it's, yes.
ReLU, you have from 0 to infinity the identity function. Here we have the step.
No. This is the CD. So no. This is GALU. This is CDF of Gaussian, and this is just part of the GALU. Does it make sense? No? Okay, let me try. So we multiply something, we multiply the value x by something by this CDF. Okay, so let's try. So here at -1, maybe we multiply -1 by, what is the value here? 0. So let me just make it sure this is 0 and this is almost 1. Multiply by 0. So here is 0. 0 minus half, it's almost 0. Okay, so 0, 0, 0. And here we're multiplying minus 0.2 by maybe 0.5. So you get some small negative part. Okay, at exactly 0, we're at a half. Sorry, yes. At 0, we're at half, but it's 0 again. And then we're multiplying by something smaller than 1. So we are, we are not exactly the identity. We're a little bit under, but then later on it approaches 1. So we multiply by 1. Does that answer your question? Okay. Any other? So this is GALU. Okay, so GALU is like ReLU on steroids and have this soft knee. That's what you might remember. If you replace GALU with ReLU in BERT, I don't think it will break. Like maybe it won't just work as well. That's just a design choice. Okay, so let's come back here. So we had this linear layer, and instead of ReLU, we had this GALU here. Okay, so we're coming through that and coming to the sum and have the residual connection. So up until here, it should be clear. Let's just have a look at the algorithm. So again, so this is what we had before. We ended up with the multi-head attention and residual connections. And now it's just making clear that, okay, this was the layer norm. Let me just come back, excuse me. So this is the layer norm here. Then there will be this MLP and then the sum. So finish the algorithm here. So the layer norm, this is the MLP here, which is linear projection through GALU and another linear projection. And this is residual connections again with the P, and there's another layer norm after that. Okay, we didn't talk about it. Yeah, there is another layer norm, which is the same functionality as here. Okay, wow. So this is just one layer of the encoder, but I guess we finished it. This is one layer. So it consists of the multi-head attention, and there are a couple of layer norms and some residual connections and linear, excuse me, multi-layer perceptron or feed-forward networks. And we repeat this for, we repeat this for first layer, then second, and up until 24 if you have enough GPU. Okay, so this is it so far. Any questions? So I guess it should be like, it's very detailed, but I'm trying to be precise. So you don't have to remember everything, but conceptually it should make it should make clear how it works internally. And I'll point, there's a couple of very cool visualization as well of these transformers online. Not about BERT, but about GPT or nano GPT. So when after we finish talking about nano GPT, I'll post everything on Discord so you can just take different perspective of understanding the architecture if you want. Okay, any questions? Great. So I think maybe we'll finish the architecture now and then take a break. Yes. Okay. So so let's sum up again what we have. So this input is a bunch of tokens. So 21, 5, 7, 8, and 3, 4. We turn it into matrix of, for this example, would be 3 times the embedding, oops, some dimensions. Then we run this through this very brutal layer of the transformer. So there's multi-head attention, several heads in parallel, scale dot product, residual connections, layer normalization, another feed-forward network, blah, 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 and end up with something which is still 3 times the embedding. But now in this matrix, through this self-attention, each token knows something already about each other tokens. This was done through through the self-attention in the scale dot product. So at the beginning here, each token has no idea what is in the other token, right? They have no idea what is in here because we just transformed them each independently by looking up in the matrix. So here we have embeddings that are like standard static embeddings. Each word, each token has its own embedding, and there's no contextual dependence. After the encoder layer, there will be learned some sort, because each token will influence the others to some extent through this learned self-attention weights. So this will now contain not only the first token info, but also like the information about the other tokens, and the same for all tokens. So it's learning now better representation of each token because it takes the context into account. And we repeat L times. So after that, we again have a matrix like 3 times the embedding. But now each token should have gotten enough information from the other tokens to have like much better representation of of itself. So here, the bank would have no chance being like polysemic in the okay. Well, bank is okay. I went to the bank. I went to the bank 5 words. So if this were 5, the word bank here would have no information about its context. Like I went to the bank, so it should be a building. But after all these self-attentions here, the representation of the bank will know that it's in the context of I went to somewhere, so it will have better representation of being a building. Okay, so this is learning basically embeddings that are contextualized. Any question? Does it make sense? Okay, cool. So this is what we have here in the last, pre-final layer. So what do we do with this final layer? So we want to turn it into something. So let's have a look at the final layers now. And okay, so Gaussian, what was the E? I don't know. Gaussian error linear units. Okay, Gaussian error linear units. I think they wanted to make something which sounds like ReLU but has different letters, so they call it like Gaussian error. I don't know. So we have GELU. Okay, so sanity check. What is this? I want to see all hands up. What is this? It's a multi-layer perceptron. 0 point, but okay, you made my day. Very good. So this is feed-forward network. Feed-forward or MLP, right? I mean, just two-linear transformation and some nonlinear activation in between. Which means this will be some sort of matrix of whatever we want. The Z will be, yeah, it could be single layer perceptron, yes. Yeah, I mean, but then the naming in the community is like, you call MLP whatever is like just stacked linear layers with nonlinearity, okay? The size will be, I guess, 3, and then the output will be whatever you specify, something like in the transformation, okay? So 3 was the example for our input, so basically this is LX, which could be 3 in the cat set. And there will be something. So here we have basically learned the learned representation again after some other transformation. Well, why not use this directly, and why to use some other projections? I don't know. I mean, this could work as well, but you want to maybe change the dimension of the embeddings to some other dimensions of your liking. Okay, so the embeddings could be, I don't know, 1,000, and this could be 500 or whatever. So you're free to choose. Basically, it's a linear projection. I think the more layers, the better. So I don't know what was the design choice here. Anyway, so we have this last learned projection. So you can do something with this output already. You can, for example, now take each token and you have its embedding in the context of the other word. So you can do something with that. Maybe we can have a very special token at the beginning. There could be like edit very special token, like, you add a special token, and maybe the special token will also learn something, as we will say later. So there's a special token in BERT, which you can use for maybe classifying the whole sentence. Maybe there's other special tokens, whatever. So each token in the input has its representation here at the end. This is the takeaway message from BERT. And we can also turn this into so-called unembedding, where we can project it into some other space, for example, so what if we project it into, let's say, LX times size of the vocabulary. So what is it going to be, this output? We take this vector, which is LX times something, and we project it into LX times size of the vocabulary. And then we applied softmax on each row. So the question is what this is going to be. So you project each token embedding into size of the vocabulary and apply softmax. What could that be? Okay, so let's take just one row. Let's take the first word cat, second word cat. Okay, let's take cat. So if you project cat embeddings to something which has a size of, so this will be a matrix, size of the vocabulary, you end up with, I'm ignoring bias here, you end up with a vector, which is the size of the vocabulary. And now you apply softmax, so you end up with a vector, which is size of the vocabulary, and this will be like a histogram. And everything, like probabilities, everything will sum up to 1. What is this? Yeah?
So remember the training objective of BERT? We are doing math, language.
Even without training, yeah, training objective will be why is this important, but basically, yeah.
So we want to compare, we want to mask input tokens, and the task is to predict the input tokens. And we will use the output right there as a probability distribution.
Exactly.
For our.
So we can turn, exactly, we are here mapping, I mean, the reason why we're doing so, yeah, maybe I should have started with the masking first before, but just, okay, I want to finish the architecture for training. But we can turn each token here, token embedding, into a probability distribution over words. So it will tell me that, you know, the embedding of cat in this context would actually map to, so here each would be like a token from the vocabulary, and what would be the probability of each token from the vocabulary. Okay, so we're turning into the probability distribution over vocabulary. We'll use this for training. I mean, okay, so maybe we'll come back to that after we talk about the masking. Yes.
Trying to predict next word.
Yes and no. So generally in BERT, we are, yeah, okay, so this would be like predicting a word. We would say, well, we would basically predict each word here, but we won't. But we can, we'll use this for later on in training. We will mask one word from the input and try to predict what the missing word was. And this is why we need a projection into vocabulary. So you were on the right direction. But without saying the masking objective, it makes no sense to talk about this. So maybe we'll come to that later. So what really matters is the output here is this learn embeddings for each token, okay? Which we can turn into something which is a probability distribution. All right, I guess this finishes our transformers. So we have the last one was the GALU and another, okay, there's another, yeah, okay, layer per norm. And here's the projection to vocab probabilities is something which we use for the training. So as I said at the beginning, you know, the output is typically embedding vector for each input token. This is what we want to use for downstream task. And in the pre-training objective, we also pass it to the projection of the, projecting to the vocabulary. So, and I guess this finishes the architecture of BERT now in full detail, hopefully. And this is, I was just like for the reference. So all the hyperparameters and parameters that need to be learned. Yeah, there's a bunch of them. So embedding matrices, position and token embedding in the input layer. Then for each of the transformer layers, there are multi-head attentions. There are what else? All these feed-forward networks, biases, and blah, 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 everything. So quite a lot of parameters to be learned. Okay, but this is basically the full algorithm for the forward pass of the BERT. And we have the graphic depiction of that. All right, so I would say let's make a break and continue then with the pre-training and fine-tuning, okay? 31, let's start 38. So let's talk about the pre-training and what the actual input is, how we pre-train the thing, and how can we train the thing for any downstream task, because there's two steps in actually using these transformers or BERT. Is something with the multitask learning we talked about last time, is that maybe there's a task which will help you to initialize your model weights, and maybe your task doesn't need any training data. And then you apply these weights, you use them for something else later on, and the model doesn't have to learn everything from scratch. It knows something about the world, but you change the objective and you learn, you have like much better cold start, okay? We have this example of multitask learning already with BERT embeddings. I mean, you can plug BERT embeddings into your network and you can let the BERT embeddings learn from scratch, basically, because it's just it's a matrix with lookup operation. But maybe if you pre-train BERT embeddings using BERT to back, well, the model will then perform better because it learned something about the semantics of the BERTs. So the same idea applies here. So the details here of the BERT is, and we might have been talking about it already. So the tokens are multilingual word piece inventory. So this is interesting because you can run. So word piece is another variant of BPE or sentence piece. So it doesn't really matter. It's like a subword tokenization. But you can run subword tokenization, for example, on multiple languages. So I think they took the whole Wikipedia and just all the languages and just run the tokenizer on all the alphabets. So this is great because then you have in your tokenizer, in your token, what they call it, not repository, inventory, your token inventory, you have subwords of English words, subwords of other alphabet words, German, whatever, Korean, maybe. I don't, yes.
If we have like the languages during the training process, we put all the words into the vocabulary of the language.
Yeah, exactly. That's I think what exactly they did. Like you take, because how you build a sentence piece? You start with the characters first. Okay, so if you have a whole Wikipedia, all languages, you find all characters, which will be the English alphabet, which will be your I don't know, Arabic alphabet, Japanese alphabet, and all these alphabets, and you start merging these together and merge and merge and merge until you reach your number of sentence piece tokens, which was like 100K. Well, originally 30,000, but now like over 100K units in 100 languages. Yeah, so you have just one huge sentence piece vocabulary, and you can basically tokenize every language, almost every sentence in any script, so to say. Okay, so this is it. This is very multilingual. So BERT can consume actually any language. Is there transfer between languages? So if BERT is trained on one language, can it do the same task in other language? It's a matter of like research question, basically. So there's research on multilingual BERT or multilingual transformers and transfer between languages. We're not going to tackle that. So we assume like we worked with one language pre-training and then the task. But there is a benefit of transfer learning learning between languages or transfer between languages from similar tasks. Anyway, so this is the tokenization. Any questions? Good. So we have the chunks. So okay, then each we have the word piece embeddings. So this is the input, right? I mean, shall I come back? Let me just come back very quickly to see these inputs. So the input embeddings. So here, input tokens and input embeddings, which is the sum of here. So here in this algorithm, we have just the token embedding and the position embeddings. There was more in the original BERT paper, but it somehow came out of fashion now. So maybe I'll mention it here. So we have this word piece embedding. So this is the first matrix. Then each position from the input is associated with the positional embedding. So this we had also. The maximum length is 500 of the BERT. So okay, this is the original BERT. The maximum length of the input was 500 word piece tokens. And if you have a longer text, which you want to put into BERT, you would basically cut it like brutally, saying like, okay, maximum length is 500. And it's been a limitation. It had been a limitation for a while, but now the models are getting bigger, and you have like long former, and so given more hardware, cheaper hardware, or bigger memory, you can make it longer. And if your text was shorter than these 512 tokens, you would basically pad it. So what was the padding again? It was like filling the rest with some sort of pad symbol. So we are like, I don't know, v pad set, and you would finish with pad, and so on until you reach 512. So I think And you would use basically, I would say you would use zeros as the index for padding because it just looks nice. You have all zeros, so it means like it's a empty text. I'm guessing that. Okay, but we talk about the special tokens. Okay, so in the original BERT paper, the first token is always a special token CLS. So you would start your sentence with a special token CLS and then do your sentence. So CLS is the abbreviation of classification. And as this abbreviation might reveal something, we will use these token for doing classification later on. So, but now we're just in the input. And what we can plug into BERT also in the as the sequence, it could be two sequences. So anyone remembers NLI or SNLI, Stanford NLI? What was that? Is a task. Does it ring a bell? Not at all. It was natural language inference. NLI, natural language inference, where you have a text and a hypothesis. Like the text would be okay, so a bunch of students is sitting in the lecture hall, and the hypothesis would be students are learning, but I don't think it really correlates, you know. Okay, so it would be okay, bunch of students is sitting in the lecture hall, and the hypothesis would be people are in a building. And this is entailment because if you know the text, like bunch of students are in the lecture hall, it entails that some people are in a building. If I say bunch of students sitting in the lecture hall and the hypothesis would be kids are playing football, I would say it's neutral because it has like completely nothing to do with each other. And if I say students are sitting in a lecture hall and the hypothesis would be students are dancing, it's a contradiction because the students are sitting in a lecture hall, not dancing. Okay, so this is a classification of two sentences. One is hypothesis and one is text. And I would, if you want to refresh this, go to lecture 1 when we introduce all these tasks. Okay, so there's like a bunch of examples in there. So if you want to represent two consecutive sequences and put them into BERT, you add a special separator token in between. So the full input would be maybe CLS, then students, blah, 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 sitting in the lecture hall. Then you would say there's a separation token. Then students are blah, blah, blah. And then there would be padding. Okay, so this is a separation. Also, if we had these two sequences, original BERT had another embedding. So we had BERT piece embeddings, positional embeddings, and it had like a segment position embedding, which would say that these tokens are from the first segment and the other are from the second segment. I guess I have an example on the next slide to make it clear. Exactly. So this is like summarizing the input. Now we are kind of, so we had it as a rows. Now we are rotating by 90 degrees to have this, the tokens as columns. So don't be confused because everybody's using different notations, columns, rows, whatsoever. So here we have the first token, and now we're using zero notation again, like for indexing from zero. So, you know, always you have to pay attention to the details, like which indexing are we using, and are we using rows or columns. But the idea here is that the first token is always the CLS. Oh, it's actually from top to down, top down. So, okay, here's an example, and it's two sentences. My dog is cute, and the second sequence is he likes playing. So here's a nice example of the sentence piece because playing is being split into two subword units. Okay, and here we're adding the first special token, the classification token, the CLS. Since these are two sequences, we're adding the separation token, and there's another separation at the end. Okay, I forgot that. So this is our token embeddings we had before. So we are looking up in the, looking up in the embedding matrix for each word piece unit, it's embedding. Then we have this positional embedding. So this is position 0, position 1, position 2, and so on. So we had these two already. And here in BERT, original BERT was also the segment embedding, basically having a two, well, for you would say it's embedding of the A segment or embedding of the B segment. And this was also like a matrix and learnable. So what is the dimensionality of this matrix? I guess it was 2 rows or 2 columns, because you have either A segment or B segment. Okay, so you have a very small matrix. Why is what important? It was important, I guess, for this natural language inference task. So you want to say which sentence comes first, and maybe for the ordering of the sentences. So segment embeddings came out of fashion a little bit. I haven't heard about them recently, but the token embeddings and position embeddings are still important for the reason, like, you need to know which token comes after which other, because otherwise in the self-attention, everything is mixed up together. So this is the input. Any questions? Okay. So now let's look at the pre-training. And BERT was using self-supervised multitask pre-training. So what is self-supervised? Well, we talked about it already many times. Self-supervised is that you create artificially some auxiliary tasks that need no labeled data. Okay, I mean, everything is supervised. Like everything in deep learning, if you want to update parameters with stochastic gradient descent, it's supervised because you want to show the gold standard data, so you can compute your loss and you can update your parameters. So there needs to be some supervision. But you can create a supervision for free just by saying, well, let's predict, I don't know, predict the next token or predict. I mean, we had prediction of next token in language models, so we learned a network. So we're saying, oh, predict a masked word piece unit. So we basically take one token from the input. Here we're coming again from bottom to top, so it might be confusing. But anyway, we say randomly, and I'll talk about it later exactly, we say, let's mask one word out here, and let's try to predict it. So this will be the one task. And now it might be clear why we're talking about this prediction of the unembedding matrix, because we want to, when we run here this prediction, we're kind of want to project everything into the vocabularies, or excuse me, the sentence piece inventory, and put a probability distribution around that to make this prediction. Okay, so this is the first task. So we're predicting missing word. Is it the same as like predicting the next word or not? Because you were talking about predicting next word. So is this task predicting the next word or not? It's not, because the word could be anywhere in the middle. And since BERT is taking information through the layers from all surrounding words, it can look into the future. Okay, very important here, very important. BERT encoder looks into the future while doing this missing word prediction. Well, we had this case before when we talk about word2vec, learning word2vec. We use the context of the word, so we have the words before and the words after. So it was also looking in the future, and we learned word embeddings of the word. So here's the same. We just mask one word in the middle and say whatever comes before and after is important for me to predict the word, because I want to learn representation for the whole input. I don't care about predicting the next word. It will be like the decoder later in GPT models, or the encoder's decoder model. But here I'm just encoding the input, and the task here is just, well, I will mask random words somewhere in the middle, and if you see all the other words, what's the word? Okay, any questions? Is it clear? Cool. So this is one task. And it's actually the most powerful task for pre-training. But BERT used also another task, which turned out to be important for things where you had two segments, like natural language inference, like this hypothesis, or excuse me, this text, and this hypothesis. So they used the second task, and the second task was a binary one. Whether the second text, so the second, well, we call it sentence, so it's not like sentence linguistically, it's just a bunch of tokens. If the second segment appeared after the first segment in the training data. So what does it mean? You take, let's say you take one, so they train it on Wikipedia. You take one Wikipedia page, and from this one Wikipedia page, you extract some random subset, not subset, it's not a set, it's just a subtext. It doesn't have to be a sentence, something like a short snippet of a text. This is your first segment. And then you extract later on, maybe after something in the middle, you extract the next segment. Could be immediately after, could be later on. I don't actually know. It could be actually right after. So this is your second segment. Okay, so one segment of text from the beginning, a second segment from somewhere later. So this would be like your positive example, because you know that the second segment came after the first segment. Or you can just create a negative example by ditching the second segment and take some random one and saying, well, this second segment didn't come after the first one in the original page. Right? You're creating a positive example by saying what's true. Well, the second segment was actually following the first segment in the original Wikipedia page. Or you just take some very random page from Wikipedia, take a segment and say like, oh, okay, this segment didn't follow the original segment in the Wikipedia page. Okay? This is a similar idea, like taking random word in word2vec. You say like, okay, the true word in word2vec is the positive example, so 1. And if I randomly choose another word, this will be 0. So this is similar. This task is a binary prediction and saying, well, did segment 2 follow segment 1 in the original page? Yes or no? Okay, does it make sense? So it learns something about like on discourse or coherence of the discourse, because if two segments are after each other, and you can predict that one text is after each other, you learn something about long-term distances and long-term kind of relevance of two pieces of text, something about coherence maybe, or discourse, or some sort of more word knowledge. If you just plug in a random text, so the model should say like, well, yeah, these two things have nothing in common, so I shouldn't, I should maybe ignore these. Okay, so this is like high-level understanding. Nowadays, I mean, it turned out that this consecutive segment prediction is important, but I mean, all the further models kind of just go with this mask language modeling idea. So mask token modeling, prediction, or learning. So this consecutive segment is somehow like out of fashion as well. But it was used in the original BERT, and in the paper you will see like when you introduce this, you get some more better performance on some tasks. But it's not the crucial part. The crucial part is actually this mask language modeling. Okay. So these were two tasks. How do you train it? Well, you have one loss here, you have another loss here. Maybe you sum them up or switch between the losses or whatever. I mean, this is a standard multitask learning, so it's easy to implement because everything is everything is differentiable. Like you create a loss, so here the loss will be okay. I want to see all hands up. So you want to your network is outputting a probability distribution, and your gold label is one-hot encoding, so it's the word from vocabulary. What's the loss you're gonna use? So last layer is a softmax, and your gold standard is one-hot. What's the loss you're gonna use? All hands. Okay, all hands. Wait a second. All hands. Oh, okay. Yeah, we haven't spoken. So you're in back? Okay, categorical cross entropy loss. Exactly. Okay, cool. So this is one loss, and this loss. Okay, well, and here, so you have a number out. So after sigmoid, you have 0 or 1, and your label is 0 or 0. So you have after sigmoid, you have something between 0 and 1, which is probability of 1, and your gold saber is 1. So what's your loss you're gonna use? Yeah, all hands. Okay, but anyway, go ahead. Yeah, it's binary cross entropy, which is somehow like it's related to categorical cross entropy if you do some little math tricks in there. Okay, cool. So we have these two losses. Maybe you then sum them up and have one loss, or just switch it. Basically, I think like they were switching the task, like training one objective for a while and the other objective for a while, and then it's basically training the weights in one or the other way. Okay, any questions? Yeah.
Unit could also be just start of the sentence token and the separator, or?
I think they're no. I think they mask the actual. So, okay, so this good question. I think they just mask the words, to be honest. But I think what I have here, the algorithm is wrong because it's taking all the tokens. So you shouldn't be. Maybe theoretically you can. I mean, because everything here, all these tokens are in your word piece thing. So you might actually predict those as well. But it makes little sense to me. So I don't know. I don't really know. It would make sense just to predict the tokens because it's masked language modeling. How it's actually implemented is a matter of, maybe it's a detail that everybody ignores so far. I don't know. Maybe, I mean, theoretically, it doesn't really matter. I guess, as long as you do some learning, you want to maybe predict like there's a. No, you would need this for this CLS thing. So most likely the tokens, but I don't know. Okay, so what was the pre-training data? I think I mentioned it already. So the entire Wikipedia in 100 languages, 2.5 billion words. So very small from today's perspective, but back then, yeah, okay. Okay, so to generate a single training instance, sample 2 segments. And for the second task, we would replace the second segment randomly in 50% of cases. Okay, so this is what I said, like you take the first segment and in 50% cases, you keep the second segment, and in 50% cases, you take some random segment from somewhere else. Okay, this is the consecutive task prediction. For the first one, they would choose random 15% of the tokens. Okay, so I guess this is the answer. So take the tokens, which might be the word tokens, not the separator and stuff like that, and then replace with the mask of 80% of these tokens. Okay, so this is, I guess they just use the actual tokens. Okay, any questions? So this is how you create your pre-training data. And here's an example. So the man went to, here we masked the word, store, separator. He bought a gallon, something missing, milk. So, and the goal would be here to predict, well, this is actually, so the second sentence was actually appearing after the first one. So the label for the second task is like true. Yes, this is the next segment. Okay. And here, an example for not consecutive segment is like the man, something to the store, penguin, something, our flight, less birds. So this looks like it comes from a random Wikipedia page. So and it's 0. So it should be like predicting 0 here. It should be predicting 1 here for this task, for the prediction for the consecutive. And we also see like the masking here. So some tokens were selected to be masked, and the model should learn what, should predict the word. So what the man went to the store, I guess. He bought a gallon of milk. I don't know. I guess so. I'm not a BERT model, but something like that should have been there in the data. Okay, so this is like how you, so this is simplified because there's no padding. The actual segments are longer. So, and these are super short segments, and they are aligned here to sentences, but they weren't sentences in a linguistic way. It's just you cut off a piece of text which is somehow long between 1 or 215, something like that. So these were not sentences. These were multiple chunks of text together, and there were sentences in there. Yes. Yeah, the masking is randomly, exactly. So you choose random, 15% of tokens you choose by random uniformly, and then uniformly, well, not uniform, uniformly 15% of tokens, and in 80% you just replace these tokens with a mask. Why is it like 15% and then 80%? I have no idea. Maybe because like they wanted to select the tokens first and then do this. These are 2 hyperparameters. How many tokens? No, it should be actually like 1 sampling in 1 shot, but this is how they did it. So basically you select some tokens and replace them with a mask randomly and uniformly over all tokens. Any other question? Okay. So here's the actually, this looks awful. Okay, but it's actually, at the end of the day, it's pretty simple. So how can you pre-train BERT in 11 lines of code? So now here we're just focusing on the masked language modeling task. Okay, so we're saying we have some input data. So these are the sequences, so n data sequences. Some parameters. We have the probability of masking, number of epochs. What is this? I want to see all hands up. What is this? More. What is this? More. It's used here. What is this? 2. I want to see 3. Okay. 4. More. People, come on. Okay, in the back. Yeah, it's a learning rate. Oh, okay. Very important concept, learning rate. Okay. So what is this? This is stochastic gradient descent. We're doing something, then we predict the loss and update the parameters. Okay, so the important part is like, what is this something? So we run this in epochs. Okay, so we run, several times. Then maybe it's ignoring batches here, but we would just implement as batches. But for each of the point in my training data, I'm gonna here the part is that with some probability I'm gonna replace the token with the mask word. And I think this is ignoring the nitty-gritty details that if in my tokens are already separator and the CLS token, that did was mean like I would replace them. Of course, that's what you don't want to do. So some care has to be taken in implementation. But basically, you go over all the tokens and say with the probability of masking, would you replace them? So it doesn't really 100% represent what was done in BERT, but this is how you, in general, do the like masking mask language model prediction or training in general encoder. Okay, so you would take a token and replace it with mask token with some probability. So okay, so we're creating the tokens. And here we keep the track of these tokens. I think I have explanation down here. Okay, so we'll explain it more. So we keep track of which tokens are we replaced because these will be our sort of like gold standard data. We want to predict the missing tokens. And once we do the prediction, we compute the loss and do the update as in standard SGD. Okay, so this is standard SGD. Compute the loss and update the parameters. But we do the prediction over the mask tokens. So this is like a high-level overview what we're doing. So let's have a look at these simple examples, lines 6 and 7. What are we doing here again? So let's say we have again the cat set, and these are the indices of these subword tokens. Okay, so these are indices in my vocabulary or inventory of tokens. So, and let's add, so the mask token would have the index of mask token is 50,001. I mean, it's just an arbitrary number. I just made it up. Okay, so maybe you have like 50,000 words in the vocabulary, and the 50,001 is the mask thing. So, and I'm going through each word. So T at position 1 is the word V, and I throw a coin with this probability, and the random outcome is to mask it. Okay, so I just replace this word by the mask token ID. Okay, so this is going to be masked. For the second one, I flip a coin, and the outcome is maybe keep. So I'll keep the original one. And for the third one, the random outcome is masked, so I'm masking that. Okay, masking this. And then I keep in this tilde T, I'll keep the indices of the mask word. So this is 1, and this is 3. So I'll use it later for the actual computing the actual losses. Okay, so I think this is easy, like self-explaining. So you just randomly mask some words and keep the indices of them. Okay, any questions? Okay, cool. So then, okay, this is interesting. So we had here line 9, this very ugly formula. Well, it might be ugly on the first sight. So this is the negative log likelihood, and we should somehow understand what the hell are we doing here in this matrix? I mean, it needs some explanation maybe. So then we exactly know what is it doing, like very precisely. Okay, so the example again is, so what we had before, the cat set. So we have these indices. This tilde n is now with these mask tokens. Okay, so this 50,001 is the replace token. All good? So this is what we did in the previous slide. So we have, this is the true input. This is the masked input. Okay, masked input. And these are the indices of the mask token. So the first token and the third token. Okay? You're with me? Cool. So what a transformer is outputting here, and this is the case where we actually map the output to, oh, let's ignore the theta, it doesn't matter, some parameters of the model. And now it's outputting, so this is the length of the input, okay, so 3. And this is what? What's the dimensionality of that? Yeah. This is the size of the vocabulary, right? So this is, excuse me, this. So let me come back here. I think it's important now to show this thing. So this is exactly this unembedding part where we took the embeddings, but then project into probability over vocabulary. Okay, so this is where we map each row into probability distribution over vocabulary. This is the output now because we want to train the prediction of the missing word. Okay, so this should now clarify this part why we talk about this. So let me come back. Won't crash. So this is the output. So for each token, I have probability distribution of words learned, mapped. And okay, yeah, well, actually I put it here. So this is the answer, of the dimensions. Okay, so it's numbers between 0 and 1 of this dimension, the Lx times size of the V, which is depicted as NV here. Okay, so each row is a distribution over vocabulary. Okay, all clear? Cool. Now let's take the T of 1. So we're iterating here. Let me come back to this algorithm. We're iterating over dimensions, over indices of these mask tokens. So we're taking, so the T's are, it was like 1 and 3. So this is the only those where we mask the token. Okay, so this is 1 and 3. So now we're iterating over the T's, and let's take the first one, which is 1. Okay, so this is summarizing again what we have. Indices of the vectors, masked indices of the vectors, and this is all the masked vectors, all the masked tokens. And this is the output of T, and this is the first row, like for T equals 1. Okay, so for T equals 1, the model should learn to predict D. So this was, remember what was the input sentence D cat set. So we mask D with the mask token. And now the model should learn what was the missing word. The missing word was D, right? It was in the first sentence, okay? Cool. So, and it has an index 21. So what is my gold vector now? So my gold vector is one-hot encoding vector, which is all zeros. And at position 21, it's just 1, okay? Right? I mean, this is how I represent a word D as one-hot encoding in my vocabulary. So this is all zeros and 1. And now my prediction is this row. This is the first row from the matrix, P. So this is how I write it, like P, first row, which is exactly this row. So this is my prediction, right? I mean, this is standard, basically a standard multi-class classification problem. I have an output of a softmax. This is my output of a network, and I have a gold standard, which is one-hot vector. And I would just want to compute you told me already the correct categorical cross entropy. Okay, so I have the first token, which I masked, and I have its true label, which was the missing word. So categorical cross entropy, something we discussed in previous lectures, is this sum. So I'm iterating over each position in the vector. So K1 to, I don't know how long it is, NV, quite a lot. And this is the definition of this categorical cross entropy. So I'm multiplying the gold standard value with the logarithm of this prediction. Well, it means for most of or actually for almost all, this term will be 0, right? Because the YK is 0 except for at position 21, right? So I can save my time, and I don't have to iterate over 50,000 zeros. But I'll just say, well, okay, at position 21, this is 1. So I just need to look at position 21, right? This is how we end up here. So this is simplified to this because I know the only one in the gold standard label is just here. I'm simplifying this categorical cross entropy. Does it make sense? Okay, so it makes it faster. We didn't talk about it before. I don't know why, but it's basically how you do categorical cross entropy over like one-hot encoding. You don't have to run for each element of the vector because this is all zeros. You just take the one where it's 1. Okay, so this is logarithm of this position of f. It's basically a logarithm of this number only because all these were zeroed out by this vector. Okay, so now we can represent this as this is just as the how we write it, the formalization. So it's logarithm of this is this is taken from the matrix. So this is the first row, position 21. Now, since we are at position T1, so we replace this one as T. Okay, so now it becomes, no, later on, it becomes T. But okay, sorry, excuse me, the 21. Okay, so we replace 21 as the, what was that? Xn and 1. Oh, why is that? Sorry, I got confused now. Oh, yeah, Xn, okay, 21 is Xn at 1. So this is the index of the first word. Okay, so Xn at 1 is 21. So I replaced it. And then I know that 1 is actually corresponds to the first position to the T. So this is how I end up with this formula. It's basically making it more abstract and abstract by replacing the indices by, making it from concrete ones in this example, making them the indices as general as possible. Okay, so if you didn't follow, I mean, just make it through again, but it should be self-explaining after you just spend some time with that. So this is how we do it for the token number 1. If we do it for token number 3, because we had masked token number 1 and 3 together, so the model should learn to predict, what was that? It was set, the cat set, which was masked. So again, I'm going to the cross entropy loss, which again means, well, most of them will be 0 because I'm multiplying by one hot vector, except for the position 5, 4, 3, 8. So I take the position 5, 4, 3, 8 from the softmax, which then turns into being the third row because T is 3, the third row in the matrix at position 5, 4, 3, 8. And again, I get the same, expression, which is a general expression based on T and the value in the input. So which means I end up with the same expression of T and Xn indexed by T for all of these positions. And that explains why I just sum them up over all these T's, which I masked. So this explains this negative log likelihood. So I'm summing up. So if I'm summing up the loss for each word that I masked, and this is exactly how that works in the detail. And I know it's very boring, like very nitty-gritty details, but if you just because this is something which you see in very many papers, like this log likelihood, and if you don't understand what it's actually the indexing is doing, then it's like, whatever, some log likelihood. But at the end of the day, it makes faster the computation of the log likelihood for each row because each of them is just one hot vector, so you don't have to multiply everything with everything. You're just indexing. So why is this fast? It's just because you're summing up something which is indexing. So indexing is fast in matrices. And while taking logarithm, you can broadcast that. And summing things together is also fast. So this is going to be super fast. Okay, so this is it. This is how the loss is computed over the masked tokens. Okay, so we computed the loss over the masked tokens, and of course we update the parameters because what we are trying to learn, we want to learn the missing tokens here, and that's how we do that. Like we replace each of them with a mask and then try to predict the missing word, and we use it with stochastic gradient descent. There's other optimizers for doing so, such as Adam. We didn't talk about it. Maybe we'll introduce it later. It's just a much faster sort of optimizing technique, but it will work with SGD as well, generally. Like SGD is, yeah, you compute your loss, get a gradient through backpropagation, and then update your weights. Okay, so this is it. And I think we'll finish on time. So any questions to this thing? Oops. Any questions? The masking language modeling? Okay, good. So now we pre-train our model. So the model now knows some weights already for, missing words. But we don't want to use it for missing words. We want to use it for sentence classification or pair of sentences classification. That's what we want. So we pre-train the model to learn some representation of words in context. But now we want to do a sentence classification. So now the CLS token comes to place. If we have task for sentence pair classification, so we have sentence 1 and sentence 2. So one of the tasks could be natural language inference and some other abbreviations which are not important. So something like where, text and hypothesis. I think SNLI or NLI is something you should remember. Text and hypothesis prediction, because you need to understand the relations between two sentences. And this is how we plug it into BERT. So as before, we have the special CLS token in the beginning. We have sentence 1 and sentence 2. And this might be, I don't know, the class could be either binary, like entitlement or not entitlement, or it could be a 3-class way, like entiles, contradicts, or neutral, as in SNLI. So, which means we use this, the embedding of the CLS token and project it to a vector of size 3, and then we'll train on this task, like standard multi-class classification. Okay, so this will be standard multi-class classification, where this would be the gold standard is one-hot encoding of the, maybe this would be 001 would be, I don't know, entailment. So you plug your sentence here, train the model, here is going to be the loss, and backpropagate the whole thing. And this is how you sort of fine-tune the model. Because the weights in the model are already pre-trained on this missing token prediction and consecutive sequences. But now, here we say, okay, we take this special token and just use it for prediction whether the whole thing is either entailment or not. Okay? Does it make sense? It's actually very, very clever. It's actually very cool because each of the tokens here has some representation of the token, but here we've created an artificial token that kind of learns everything from the sequence, that learns the task. So it's kind of cool. So this is how we represent one task, but we can, so this explains the special CLS token, but we can use the BERT for doing more stuff actually, because why not? We can do single sentence classification task, of course. So it should be like, I don't know, sentiment analysis. So is the movie positive or negative? So it could be binary, where we have only single sentence. And the only difference is like we just, we have the CLS token at the beginning as well again, but there is no separator in between because this is just a single segment. And again, we say, well, okay, here, this will learn everything from the whole sequence. And I'll just plug here, I don't know, maybe just sigmoid. Why not? So it's going to be binary, positive or negative. And I train the whole thing on my data set, like IMDb, for example. I train this, and it's already pre-trained. So there are some weights already known, again, on this missing word prediction, so the mask language modeling. But I can fine-tune it. So it's important. Okay, fine-tuning. I'm fine-tuning. I'm changing the weights on my supervised task. And the task is different from mask language modeling. I mean, it's just saying, well, is the review positive or negative? It's different from, oh, what is this missing word? But through this missing word, the network learned, self-supervised quite a lot about language and the world, maybe, somehow. So it really helps me quite a lot for my downstream fine-tuning task. So it's like word embeddings on steroids, because these are contextual word embeddings. Okay? So this is another task. And you see, I'm using the same architecture. So I pre-trained BERT on on this mask language modeling, but I can use it for expressing two sentences classification, single sentence classification, and more, because for each token, I have its corresponding word embedding, and excuse me, and I can do something. So, okay, what is this? O, B pair, O. What is this? This is a task. Okay, don't look here. What is this task? So it's predicting something for each token, and the something is either O or B per or O. So, and the other task could be, let me just say, like E per or B orc or E orc and stuff like that. What's this task? Maybe you see it here and there. Okay, what is that? I want to see all hands. Yes? Or we're predicting whether the token is a person or organization. We're using B and I for what? What's the difference between B and I? So maybe the thing is not just single token, but maybe multiple tokens. So I need to predict whether the organization starts with this token and then it's inside the token. So begin and inside. Okay, we're getting somewhere. So we're predicting person, organization, and stuff like that. So what is this? I want to see a few hands. Okay, named entity recognition. Yeah. I mean, you've heard it. Okay, so named entity recognition means classifying each token into one of these things, and it's an instance of something else. So what is, okay, named entity recognition, or we can do here this. What was that? Part of speech labeling. Part of speech, because we can say also for each word, for example, oh, this is a noun, this is a verb, this is a noun. Yeah, so, and all these, so NAR and POS belong to something which is called sequence classification, right? We classify a sequence of tokens, and each of them will classify into something, either whether it's O or person or whatever, so these text set or part of speech and stuff like that, okay? So remember this, important, okay? Cool. And again, I mean, we're using the same pre-trained model, but now the supervision will be different. Like we'll have gold standard data for each of these tokens, so we can put a classifier, so to say, the softmax on each of the outputs here, and then do the loss over, like sum the loss of over all the words. So again, fine tuning. So we fine tune it on sequence classification. So this is pretty cool. We have one model pre-trained. We can run it on 2-sentence classification, single sentence classification, and sequence labeling. This is pretty awesome. Okay. So now, how is it complicated to pre-train this thing on this mask language modeling? We'll finish in 2 minutes. Okay. So originally, it took them 4 days on 64 TPUs. So TPUs is some like GPU from Google. They call it Tensor Processing Unit, and you can just access it on Google. And then again, once pre-trained and so this is transfer and fine-tuning on your small data task. And they actually, the results that we're getting from BERT back then in 2017, 18, 2018, 2019 was really like a super, not super performance, but the difference between the performance state-of-the-art models and using BERT was super huge, like really a big increase in performance because of this pre-training. So you don't have, I mean, you can train your BERT if you want on academic budget. So if you're really interested, there's tricks how to pre-train your BERT on a single GPU in a day or something like that. You will sacrifice something, the performance won't be like on some tasks, maybe not 82.4%, maybe 81.7%, but maybe that's something, maybe it's worth the effort. So it can be done more efficiently. So recap. So the clever concepts we are talking is there is quite a few of them, and they're mastered in a single model. And if you're interested more on internals, how the BERT works, I highly recommend to look into this paper, A Primer on BERTology, appeared in Tackle quite 3 years back by Anna Rogers and her colleagues. It's highly recommended. It's a very accessible reading. It's highly recommended, and you will learn quite a lot about BERT because it's one of the milestones in NLP and deep learning. Why it's like this big wave. Having said that, that's all for today. And next time we start talking about decoder language, decoder transformers such as GPT and maybe encoder-decoder transformers. But the encoder one is simpler in terms of the self-attention. And in terms of there's no so-called masking. Well, there is masking of the missing words, but the actual internals of the self-attention have something which is called masking, which we'll talk about later on. So it's better. I highly recommend to go through this lecture again so you understand the transformer architecture, because with the masking it's going to be more complicated a little bit, so that you won't struggle that much. Any questions? All right. Thanks a lot and have a great weekend.